Ever get that feeling like you want to prove something you know, but without having to lay out all your evidence?
Oh, yeah, I know what you mean.
Like, say, proving you were at a particular place yesterday without showing like your entire location history for the past week.
Right, right, like selective disclosure.
Yeah, exactly. Selective proof. And that's kind of the jumping off point for our deep dive today.
Cool.
We're going down the rabbit hole of zero knowledge proofs, or ZKPs.
Ooh, ZKPs, fascinating stuff.
It's like one of the most fascinating things in cryptography, at least to me.
Yeah, definitely up there.
Being able to prove, something without actually revealing the thing itself.
It sounds impossible, but that's the beauty of it. Zero knowledge proofs or ZKPs, they're like this really clever set of techniques, right?
Right.
So you have like one person, we'll call her Peggy.
Okay, Peggy.
She wants to convince another person, we'll call him Victor,
Victor.
that some statement is true.
Okay, so a statement, not like a physical thing, but some piece of information.
Exactly, a piece of information. And here's the kicker. During this whole process, Victor learns nothing except for the fact that, hey, Peggy's statement is actually true. That's it.
So he doesn't learn any of the details that support the statement.
Nope. Just the validity of the statement. It's all about proving something without revealing anything extra, maintaining that privacy. It's wild, right?
Yeah, so privacy is baked right in. So our mission for this deep dive, I guess, is to really wrap our heads around ZKPs, but like from a high level, yeah.
That's the plan.
We use analogies, come up with some mental models so we can really visualize what's going on.
I like it.
We're going to stay away from the heavy math. No complex formulas here.
Phew, good, because I'm no mathematician.
And no crazy technical jargon that'll make your head spin. We just want to make this interesting and understandable for everyone.
Absolutely.
Okay, so maybe let's start with like the basics of any proof, especially this interactive kind of proof,
Good point, yeah. Usually when we think proof, especially like in math, we think of something static, right?
Yeah, like written down step by step.
Exactly, a logical flow. But these proofs, they're more like a conversation.
Oh, that's a good way to put it.
They involve back and forth between, like we said, Peggy and Victor.
So instead of just handing over evidence, it's more of an exchange.
Right, more interactive, like a challenge and response sort of thing. Victor asks Peggy questions or gives her tasks related to her claim.
Okay, so Peggy's got a secret, Victor wants proof, but she can't just come right out and say it. What makes this interaction, this proof game, actually convincing? What are the rules?
So there are a few crucial things a proof system needs to have. First up is soundness.
Soundness, okay.
Basically, this means Victor shouldn't be convinced by something that's false. If Peggy's trying to pull a fast one, if her statement isn't really true, the system needs to have a way for Victor to catch that, to see through the bluff.
Gotcha. So like Peggy can't trick Victor if he doesn't really know the secret.
Exactly. Soundness is all about protecting against fake knowledge, false claims.
Okay, makes sense. What's the other important rule here?
The flip side is completeness.
Completeness, okay.
If Peggy's statement is true, she should always be able to prove it to Victor.
Through this process, this interaction.
Yeah, like if Peggy genuinely isn't colorblind, she should be able to prove that using whatever method they agree on.
So soundness prevents lies.
Yeah.
Completeness guarantees that truth can be shown. That's a pretty good base. So where does the zero knowledge part come in? That's the real mystery here, right?
Absolutely. You hit the nail on the head.
Okay.
The third crucial requirement is zero knowledge.
Zero knowledge.
This means that throughout the entire back and forth between Peggy and Victor, Victor only learns one thing.
One thing, okay.
Whether Peggy's statement is true or false.
That's it.
That's it. He doesn't get any extra information, no details about why it's true, no hints about the secret itself.
So he can be sure it's true, but he doesn't know how it's true.
Exactly. He learns nothing beyond the yes or no, true or false. That's the heart of ZKPs. Proof without revealing the what.
I'm starting to see the magic here. So like these interactive proofs are a super specific conversation where only a yes or no is revealed.
That's a good way to think about it, yeah.
Okay, I think I'm with you so far.
Perfect.
So let's dive into some of those examples you talked about, those toy examples, to see zero knowledge in action.
Yeah, let's do it. They're great for building intuition.
Okay.
Let's start with the colorblind test.
The colorblind test. Oh.
So imagine Peggy has two balls that look identical, at least to Victor.
Identical. Right.
Victor, for the sake of this example, is totally colorblind.
You can't see any color.
None at all. But Peggy, she sees that the balls are different colors.
Oh, interesting.
Victor turns around. Peggy either swaps the balls between her hands or she doesn't. She keeps them the same.
Okay.
Then she shows the balls to Victor and asks, "Did I swap them?"
Now, if he's colorblind, he has no idea if they're swapped, right?
Exactly, because they look the same to him. But here's where it gets interesting. Imagine they do this over and over again.
Many times.
Victor just guesses randomly each time. Did she swap? Did she not? If Peggy is also just guessing, she'll be right about half the time. Pure chance.
50-50.
Right. But if Peggy consistently knows whether or not he swapped them, even though the balls look the same to him, Victor starts to get really convinced.
Convinced that?
Convinced that Peggy isn't colorblind.
Right, because she's guessing way better than chance would allow.
Exactly. Her success rate is the proof.
Okay, but where's the zero knowledge? That's the key here.
Here it is. Victor never learns the actual colors of the balls.
He just knows she can tell them apart.
Yep, he only learns that Peggy can distinguish between them. He doesn't know what those colors are, only that she sees a difference.
So he gets confirmation of her ability, but not the details of how it works.
Precisely. He doesn't learn anything about her vision or the specific colors, just that she can differentiate them.
That's a really cool way to think about it. It's like proof of a capability without knowing the mechanics.
Exactly. What about the other classic example, the ring cave?
Yeah, let's go there.
Okay, so picture a cave, right? Shaped like a ring with one entrance.
A ring-shaped cave.
So on the other side, there's a gate, a locked gate connecting the two halves of the ring. This gate, it only opens with a secret word.
Okay, and only Peggy knows the word.
Only Peggy. Now, she wants to prove to Victor that she knows the word, but obviously without actually telling him what it is.
Sounds like a riddle.
A bit, right.
Yeah.
So Peggy goes into the cave. Victor's at the entrance. He can't see which way she goes, left or right.
He just sees her disappear into the cave.
Right. Peggy walks around, and if she takes the path with the gate, she uses the secret word, opens it, and keeps going.
So she might just go in a circle, or she might go through the gate.
Exactly. Then Victor shouts out aside, "Come out on the left," or "Come out on the right."
And if she knows the word, she can always come out the side he picks.
Exactly. If she consistently comes out where he tells her to, over and over again, Victor knows she must know the secret word to open that gate.
But he still never hears the word itself.
Nope. Never. That's the zero knowledge.
Yeah.
He only sees her emerging from a path, not how she got there. No information about the word itself is revealed.
It's like proof by action, not by telling. I like these examples. They make it very concrete. Okay, so proving you can do something because you have this secret knowledge without revealing the knowledge itself.
That sums it up perfectly.
You mentioned this idea of formalizing the idea with something called interactive Turing machines. That sounds a bit more technical. What's the takeaway for us regular folks?
Don't worry, we'll keep it high level. When cryptographers, the folks who design and analyze these systems,
The pros.
yeah, the pros, when they want to be super sure these interactive proofs work the way they're supposed to, they use theoretical models.
Like a blueprint.
Yeah, exactly, like a blueprint for computation.
Yeah.
And interactive Turing machines, or ITMs, that's one of their tools, think of them as a way to represent two computers.
Are Peggy and Victor.
Exactly. These computers, they can send messages back and forth, and the whole thing is very precisely defined.
So they know exactly what each player can do.
Right, and they can rigorously test the system. Can Victor be tricked? Can Peggy always prove her claim if it's true?
It's about having a really solid foundation, making sure the proof system is actually secure.
Exactly. And within this model, they can define what soundness and completeness really mean in a very specific way.
So it's not just hand-wavy, it's very precise mathematically.
You got it. You also brought up something else interesting. Interactive proofs, being able to prove things that are outside of the easily verifiable category.
Yeah, I caught my eye.
It's pretty cool. You see, in computer science, there's a category of problems that are pretty easy to check if you have the answer, but really hard to find the answer in the first place.
Okay, I think I follow.
And what's fascinating is that interactive proofs can be used to prove stuff about problems that are even harder than those, in a sense. It's like they unlock this whole new level of proving things.
Wow, so they're more powerful than we might initially think.
Right, and you had a great example, graph non-isomorphism.
Yeah, what even is that?
It's about figuring out if two networks, let's say two social networks, have the same underlying structure, even if the names of the people in them are totally different.
So like same connections, different names.
Exactly. If they don't have the same structure, we say they're non-isomorphic. And figuring out if two networks are non-isomorphic, that's thought to be a very hard computational problem.
Okay, so it's not easy to just look at them and tell?
Nope. So how could Peggy prove to Victor that two social networks are structurally different without revealing all the specific connections? That's where LeakAPs come in.
Right, because showing him all the connections would give away too much information.
Exactly. In a zero-knowledge proof for this, Victor takes one of the two networks and he scrambles it up, changes all the names.
Like giving everyone a random code name.
Perfect analogy.
Hmm.
Then he shows this scrambled network to Peggy. Now, Peggy, she has some way of analyzing the original structure.
Just got her methods.
Right. And she tries to figure out which of the original networks this messed up one came from. If the two original networks are truly different, then the scrambled one will only match one of them.
So she should be able to tell, even though it's all mixed up.
Exactly.
And if she gets it right every time.
Victor gets more and more confident that the two original networks were indeed different, non-isomorphic. But here's the key. Victor never learns how the networks differ.
He just sees her succeed at this identification task.
Right. He doesn't see the underlying connections, the blueprint, just the result. And this is for a problem that's considered pretty hard to figure out in the normal way. ZKPs are powerful.
That's really impressive. It's like she can see the secret structure without showing it. And you mentioned this idea of a simulator, which is really key to zero knowledge, right?
Absolutely. The simulator helps us understand what zero knowledge really means. Imagine Victor, right? He's trying to be sneaky. He wants to learn more than he's supposed to.
More than just true or false.
Right. The simulator's like this. Can we create a fake Peggy?
A fake Peggy, okay.
A computer program, essentially.
Right.
That can have a conversation with Victor that's indistinguishable from a conversation with the real Peggy.
Even though fake Peggy doesn't know the secret.
Exactly. If we can make such a simulator, then whatever Victor sees in the real interaction, it can't have revealed the secret.
Because he could have had the same experience with someone who didn't know it.
Exactly. It's like a magic trick. You see the illusion, but if someone who doesn't know the method can create the same illusion, you haven't actually learned anything about the method itself.
I like that. It's a good way to think about it. If you can fake it perfectly, the real thing isn't leaking any information. And you talk about two types, perfect zero knowledge versus computational zero knowledge. What's the difference?
It comes down to how good the simulator is. In perfect zero knowledge, the simulated conversation is identical to the real one. Statistically, it's impossible to tell them apart, even with unlimited computing power.
Wow, perfect.
It's really strong. Like the graph isomorphism example, that can achieve perfect zero knowledge. But getting perfect zero knowledge for all kinds of interesting problems is really hard.
Makes sense. It sounds like a high bar.
That's where computational zero knowledge comes in.
Computational, okay.
Here, the simulation isn't perfectly identical, but it's so close that no realistic computer could tell the difference.
Like a twin, but you'd need a supercomputer to spot the difference.
Perfect analogy. And this relies on the fact that some computational problems are just really, really hard to solve, like trying to guess a super long random password. It's practically impossible.
So it's secure for all practical purposes, right?
Exactly. And that's usually what we can get in the real world, and it's still incredibly valuable for security.
Okay, computational zero knowledge is like the workhorse of ZKPs then.
Pretty much, yeah.
Now, you also bring up this idea of bit commitment as a sort of building block for more complicated ZKPs. What is that and how does it fit in?
Bit commitment is like a digital version of sealing something in an envelope. Say Peggy wants to commit to a single piece of information, just a 0 or a 1. She wants to reveal it later, but not now. And she also wants to make sure she can't change her mind once she's committed.
Like a promise that can't be broken.
Exactly. So she puts her secret bit into a locked box and sends the box to Victor.
Back to the locked boxes.
They're helpful, right?
Yeah, definitely.
So Victor has the box, but he can't open it. He doesn't know the bit. And because it's locked, Peggy can't change it either. Only when she gives Victor the key can he see what's inside.
So it's like setting your choice in stone, but keeping it hidden for a while.
Exactly. Now, in cryptography, we achieve this with things called one-way functions. They're kind of like a blender. You put stuff in, it's easy to blend it up, but impossible to get the original ingredients back out.
You can't unblend a smoothie.
Nope. These functions let Peggy lock the box easily, but Victor can't unlock it without the key, and Peggy can't change what's inside. And this bit commitment idea, it's a crucial tool for making more complex zero-knowledge protocols because it lets people make commitments without revealing the information prematurely.
Okay, so it's like a foundational piece, a building block.
Exactly.
You then give this example of a ZKP for a hard problem called Graph 3 colorability. Break that one down for us.
Sure. Graph 3 colorability is all about, well, coloring. You have a network, think of it like a map, with cities and roads connecting them.
Okay, I can visualize that.
The problem is, can you color all the cities using only 3 colors?
3 colors, all right.
But here's the rule. No 2 directly connected cities can be the same color.
So, like, if 2 cities share a road, they got to be different colors.
Exactly. Now, this problem, figuring out if you can color a map this way, it's really hard for computers to solve if the map is big and complex.
It sounds deceptively simple, but it's not.
Not at all. But let's say Peggy knows of valid 3 coloring for a network.
She's found a way to color it that follows the rules,
Yep, and she wants to prove this to Victor without showing him the entire coloring scheme.
because that would give away too much, right?
Right. Back to our log boxes. Peggy puts each city's color, red, green, or blue, in a locked box. 1 box per city, and she sends them all to Victor.
A box of secrets for every city.
Exactly. Victor wants to check if her coloring is legit. So he picks a random road connecting 2 cities and asks Peggy to open those 2 boxes.
He's testing a random connection,
Yep. And Peggy opens just those 2 boxes.
not any others.
Right. Victor sees the colors, checks if they're different. If they are, that road is colored correctly. And here's the zero knowledge part. Victor only sees the colors for that road. He doesn't see the whole map's coloring. And, crucially, Peggy could have chosen any valid 3 coloring to start with.
So even if they did this multiple times, he wouldn't necessarily learn the full picture.
Exactly. By repeating this, picking a random road each time, Victor gets more and more confident that the whole map is 3 colorable, but without ever seeing the complete solution.
He sees enough to trust, but not enough to copy.
Exactly.
Okay, I'm starting to see how ZKPs can work for these really complex problems, all while keeping information private. So let's bring it back down to earth. Why should we care about ZKPs in our daily lives?
That's the big question, right?
Yeah, what are the real-world uses for this stuff?
Great question. ZKPs are not just a theoretical curiosity, they're being used in real applications where both security and privacy are super important.
Okay, give us some examples. Where might we actually run into this technology?
One big area is digital signatures.
Digital signatures.
You know how you sign a document online? Well, Schnorr signatures, they use zero-knowledge principles to let someone sign something digitally and prove it's really them, and that the message hasn't been tampered with, but all without revealing their secret signing key.
So I can prove it's me without giving away the thing that proves it's me.
Exactly.
That's pretty wild.
It is. It's a much more secure and private way to verify digital identities.
Okay, big implications for online security. What else?
Another cool one is Secure Remote Password, SRP. It's a way to log in to a website or an app, but with a big privacy boost.
Okay.
The server, the website, never actually sees your password in plain text.
They don't store it.
No, it's never even transmitted directly. Instead, they use a ZKP-like exchange to verify that you know the password without actually sending it over the wire.
So even if hackers get into the server, they can't steal a bunch of passwords.
Exactly. Much, much safer against breaches.
Huge improvement, yeah.
Oh, and there are zero-knowledge range proofs. They let you prove that a number, your secret number, falls within a certain range.
For a range of numbers, so cool.
Right, like proving you're over 18 without giving your exact birthday, or that your bank balance is above a certain limit without revealing the exact amount. Things like Peterson commitments are used in these proofs.
So you can meet requirements without oversharing.
Exactly. It's huge for privacy-preserving systems, like anonymous transactions in cryptocurrencies.
Or even like private online voting.
Exactly, you got it.
So ZKPs really are about more secure and private digital interactions across the board.
Exactly. It's like a paradigm shift in how we can trust and verify things online, all while prioritizing privacy in a way that wasn't possible before.
This has been a really fascinating deep dive. I feel like I have a much better grasp on zero-knowledge proofs now. The idea that you can prove, something without saying what you meant. It almost seems like magic.
Right. It's one of the coolest things in cryptography.
And they're being used more and more, not just some theoretical idea.
Absolutely. While the math behind it is still pretty complex, the core ideas and the possibilities they open up are huge, and research in this area is booming.
It's an exciting field. So as we wrap up here, think about this. What other situations can you imagine where being able to prove something without revealing extra information could change how we do things online, how we build systems?
Lots of possibilities, right?
Yeah. ZKPs really point to a potentially more private and secure future. Thank you for joining us on this deep dive. We hope you learned something new and interesting, and we encourage you to explore the world of cryptography and zero-knowledge proofs even more. Until next time.